way, strolling so casually. We're different and the same. Gave you another name. Switch up the batteries. If you gave me a chance, I would take it. It's a shot in the dark, but I'll make it. Knowing the little hope, you can't shame me when I am with you. There's no place I'd rather be. No, 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 no place I'd rather be. No, 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 no place I'd rather be. No, 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 no place I'd rather be. We set out on a mission to find our inner peace, make it everlasting, so nothing's incomplete. It's easy being with you, sacred simplicity. As long as we're together, there's no place I'd rather be. With every step we take, Kyoto to the bay, strolling so casually. We're different and the same. Gave you another name. Switch up the batteries. If you gave me a chance, I would take it. It's a shot in the dark, but I'll make it. Knowing the little hope, you can't shame me when I am with you. There's no place I'd rather be. No, 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 no place I'd rather be. No, 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 no place I'd rather be. No, 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 no place I'd rather be. When I am with you, there's no place I'd rather be. Yeah.
So today we are going to shift it a little bit on more software oriented, because one thing I think I failed to do last time is that if you are aware that we have code demos almost every lecture except for the last one, and I feel really sad about that. So today we are going to give you a lot of code demos if we can catch up on time. But you know, before we start, it's always a good idea to remind ourselves where we are coming from. So the first thing that you have to be aware is that every processor that you are dealing with today are also called pipeline processors. And whenever there are pipeline processors, there are three different types of hazards that we have to deal with, no matter in hardware or in software. And the three types of hazard we have today is like structural hazard, meaning that two instructions need to access the same pieces of hardware. However, the hardware unit that we are accessing cannot allow concurrent access of both. So it turns out that one of the instructions has to wait. And the other one is control hazard, means that, well, most of the time, if we want to continue generating outcome for instructions, you need to continuously getting inputs. But there are chances like, well, there is some kind of if else condition, or there might be function call. You are not sure if we are calling it or not. And sometimes there would be exceptions that you don't know where the next instruction is going to be. So it turns out that there are chances that, well, your program counter are changing all the time. However, you cannot fetch the right instruction immediately until you know the result of the previous execution. So that's called control hazards. And the other one is called data hazard. It means that, well, the instruction is depending on the outcome of another instruction. And turns out that you won't be able to get the right execution outcome of your program if you don't follow that order. So there are, and that's the 3 types of hazards that we have. And to address those hazards, we have seen quite a few mechanisms. So stall is the universal solution. However, we don't like it because it's just make your program terribly slow. And there we are. So for structural hazard, well, since the source is because your hardware doesn't support concurrent access, so you need some mechanism in the hardware to make it happen. In terms of control hazard, there is no better thing that you can do other than prediction. However, whenever there is a prediction, there's also the cost of misprediction, which you also experience from a few demos and probably your homework as well. And for data hazard, we have been talking about data forwarding, and also through dynamic instruction scheduling, we can reorder the instruction to cover the latency when we are waiting for the outcome of another instruction. So those are the ways that we have been seen so far to address those hazards. And as a recap, remember that was the hardware that we were dealing with in the past. There's no data forwarding, and so in terms of data hazard, the only thing you can do is to stall. And now with data forwarding, we are supposed to restart the execution of any instruction at any time when the data is available. However, sometimes you just couldn't do that because you have to follow the strict order of your compile instruction. And well, and this problem is even worse if you have superscalar in your processor. And what does that mean by superscalar? It means that we are widen the fetch width and decode width, as well as the ability to execute or say issue more instructions at the same time. And theoretically, with the amount of increase, the amount of parallelism you increase in your hardware, you are supposed to get that kind of benefit. However, most of the time we can't because there is no way we can fully utilize our hardware if we have to follow the strict ordering of your compiled program. So it turns out that we want to reschedule our instructions according to the order we want. However, there are things like false dependencies preventing us from making that happen. So it turns out we figure out that, well, the reason why we have false dependency is just because we don't have sufficient amount of space to store those temporary results. So what if we decouple the architectural registers and the physical registers and allow the instruction to temporarily store their outcome in the physical registers when we are executing those instructions? So it turns out here is the register renaming hardware out of the execution pipeline, which means that, well, now your processor not only able to fetch multiple instructions, decode multiple instructions. In the meantime, you can also rename your instructions in a way that by renaming, you rename your output register to a temporarily or say physical registers for the outcome. And you have a reorder buffer. And the reason why we want to have reorder buffer is because remember, we still have branch, and branch could be mispredicted. We still have exception, which may occur at any time during execution. So we still have to guarantee the order of instruction when we present those results to the programmer, to the software. However, internally, with this hardware, we are able to reschedule our stuff really as the data dependency order. So that's the overall design that we are sitting with. And with that, we have run through an example like this, which we try to use the register renaming logic, and then we schedule the instruction execution like the pipeline that I draw here. And once we go through this, we figure out that, well, with this register renaming pipeline, it indeed can do out of order execution. But sometimes there are limitations, like when we found more than 2 instructions to execute. However, since our hardware can only put 2 instructions into execution, then there is no way that we're still limited by that. However, it's already better than the previous proposal. And the other thing is that if you look at the finish of those instructions, you will figure out that after some point, although we still have the limitation of issue width equal to 2, however, we indeed fully utilize that issue width in a way that right now we have CPI equal to 1/2, which is 0.5. So that's where we were in the last lecture. And today we are going to continue our discussion on out-of-order dynamic instruction scheduling. And then after we finish that part, we are going to see how we can program better on modern processors. So last time we talked about register renaming pipeline, and some of you were thinking about, oh no, the pipeline diagram is too complicated for me to draw. So today I'm going to start with 2 different kinds of analysis that you can probably use it it's easier to understand. So a few things that we can mention. So first of all, right, we mentioned that for this processor that we are talking about right now, we say the issue width is 2. What does that mean by issue width equal to 2? It means that at any cycle, you can only put 2 instructions into execution. What does that mean by 2 instruction into execution? So saying that if I have a lot of instruction that can be executed at the same time, I can only pick 2. And typically, because we want to preserve the program order as much as possible, so we would pick the first 2. And another implication is that, well, if you can also consider now your processor has multiple execution pipelines. So for example, like this particular processor that I drew in the previous slides is that you have an integer pipeline that can execute simple integer instruction. You have a pipeline for branch instruction, and you also have a pipeline for memory instructions. And by issue width equal to 2, it means that only 2 of this can have an instruction in its very first stage for execution. So now let's look at the very beginning of the 4th cycle. So this is the time we have all instructions in the instruction queue already. Well, not all instructions, but sufficient amount of instructions in the instruction queue. So you can see right now we have 4 instructions that we can pick, right? And within this 4 instructions, the first 2 that we haven't executed and they are able to execute are 1 and 2. And for 3, from the analysis, 3 is depending on 1 and 4 is depending on 2. So you cannot execute them right now. And so it's an obvious decision that we can put 1 and 2 into execution at this time. And then for the next cycle, what happened is that, well, you can see that we can move instruction 1 to the second stage of the memory pipeline, because it's once you enter the pipeline, you can keep making progress. And for the 5th cycle, in the meantime, we can pick 1 more instruction to execute. That is instruction 4, because remember, for 2, it will generate its outcome just 1 cycle, right? So in the beginning of the next cycle, you can start enjoying the outcome of instruction 2. So you can put 4 into execution. And in the meantime, you also get instruction 5 and 6 decoded and fetch 9 and 10, right? So now, in the next cycle, in the following cycle, which is 6, given that we have 5 and 6 in the instruction queue, right? Which one are we? Well, we have 1, 2, 3, 4, 5, 6, right? And those are all available for you to pick. And we already have instruction 1 finishing its M2 stage. So which means that anyone, depending on instruction 1, can now be executed. So who is the one depending on 1? 3, right? So right now you can imagine we can put 3 into execution, right? And 3 is an LU instruction. So 3 should be here. And then and the other thing that you can potentially do is that you can also execute 5, because 5 is depending on 4. And 4, although here I put it in a dash stage, means that, well, it's done execution and it's actually not doing anything at this point. And we have to wait for the completion just because we want to maintain the program order. So this is, you consider now, this 4 instruction is done and it's already in the instruction queue. So anyone who, depending on 4, can enjoy its outcome. So that's 5 can be executed at this time. And at this point, we already got 2 instructions into execution. So there's nothing we can do with 7 and 8, even though they can be executed. Now, in the meantime, we can write back 2 instructions because we can also complete 2 instructions at the same time. Then in the next cycle, right, we have 1, 2, 3, 4, 5, 6, 7, 8, right? And we have executed up to 5. So within these 3 instructions, which one could be executed? What is 6 depending on? Six is depending on 2, and does 2 finish? Yes, right? So we can actually put 6 into execution, right? And for 6 is a memory operation. So it could be in the memory pipeline now, right? And well, we only issue 1 instruction, so we still have 1 more slot. Can we execute 7? Can we execute 7 now? RDI. When was the last time we update RDI? 2, right? Has 2 finished? Yes, right? It has been finished way back. So 6 and 7 could be executed, and 3 and 5, they will advance to their next stage. All right. Now, for cycle 8, now every instruction is here, and we have executed we have put everything up to 7, so we can pick from this 3, 8, 9, 10. So 8, 9, and 10, who can be executed? Can we execute 8 now? No, why? Depends on 6. Can we execute 9? 9 is depending on RDI. And when RDI can be generated. 7, is 7 done? 9 yet? Can we forward the value? Right. So 9 could be executed, right? So 9 could be executed and 6 could advance, right? And finally, in the next cycle, as a lot of you could imagine, we can put 8 and 10 into execution, right? So that's another way of solving this kind of problem. Okay. So yeah, and if you keep drawing the pipeline, you will figure out that after some point, right, your CPI is equal to 0.5 because you are retiring 2 instructions every cycle. Okay? All right. So one more way of looking at this problem. Another way to do this is through data flow graph analysis. And now I keep iterating this one. So I would have like 20 instructions here that you can play with, right? So again, assuming right now you have two instructions that's already executed, decoded in an instruction queue. So at this point, can you see any instructions being executed? No, why not? If they are already coded. Right now, okay, assume that this is what you have in the queue. Can you execute one or two? Given that we have registered remaining hardware, they are all renamed right now, and they are ready for you to pick. Right, both of them could be executed, right? Now, with the data flow graph, right? Next cycle, we are going to decode 3 and 4. With the data flow graph for 3, what is it depending on? 3 is depending on who? Instruction 1. And it takes 2 cycles for instruction 1 to generate the outcome, right? So, well, assuming this is the cycle as well, right? So this is cycle 0, this is cycle 1, cycle 2, right? So you have to wait for 2 cycles, which means that you can only start executing instruction, right? So you can put 3 here, right? And for 4, right? Because it's only depending on 2, and 2 the next cycle, right? So you can feel free to execute 4, right? Now, for this cycle, cycle 2, we have 5 and 6, and we already put 3 into execution. So there's 1 slot left for the 2-issue pipeline. Are you picking 5 or 6? Which one can you pick? Which one are you going to pick? 5 or 6? Actually, you can do 6. You can't. Why? Because you only have 1 slot and you can only pick one, right? And if you can only pick one, you have to pick the earliest one, right? So 5 gets executed. But you are right. In the next cycle, we can start executing 6, right? So 6 occupied Okay. Okay, so 13 has to wait for 2 cycles later, right? And so that's why it's scheduled here. And 14 is right here, right? And now we got 13 and 14 into execution, and we received 2 more instructions, 15 and 16 at this time. And if you look at 15 is depending on 14. So it could only be 1 cycles later. And if you look at 16, right, it could actually be executed at this time because 16 is only depending on 12, right? So at this point, right, you still got 1 instruction, 16 to be executed, and 15 have to schedule later. And now the next cycle, you receive 17 and 18. However, the issue slots are queued by 13 and 15. So you cannot do anything. Now, and for 17, it's depending on 12. And but in the next cycle, as soon as we have issue slots, you should execute 17. So that's why I put 17 here. And 18 is depending on the outcome of 16, which is 2 cycles later. So you can put 18 2 cycles later. So right now, when we get 19 and 20 in the instruction queue, 17 and 18 are executed, are in the issue slot. So there's nothing we can do with 20 and 19. But you can always execute 20 and 19 later. So that's the data flow graph analysis. And through this one, you can see it's 0.5. Yes.
Jump instructions, right?
What?
Some of them are jump instructions.
Yes.
So are we assuming that the jump is not taken in this case?
Well, so in this case, right, we are assuming that we have a perfect branch predictor already, right? So that's the assumption that we in a question, right? So right now, well, again, right, with the same so we have show you 3 different ways of looking at the execution of the same code pieces, and they will give you the same outcome, and you can use them interchangeably. But one thing you will find that they all tell you that for these pieces of code, we have 2 instructions that we can execute at the same time, right? And we are fully utilize the superscalar pipeline for with out-of-order scheduling on these pieces of code. So that's what we learned, right? And one thing that's interesting is that you can also find the program, the execution time, the latency is completely depending on a certain chain of execution, which is this one, right? Which is 2, 4, 5, 7, 9, 10, 12, 14, right? You will see the execution is depending on this sequence of instructions. It's completely depending on this sequence of instruction, right? So, and for other instructions, right, no matter how you schedule them, they typically don't affect the end-to-end latency of the execution, right? So right now, you might want to have a feeling that, well, there are some instructions that are critical to my program performance. So if you want to improve the program performance, you have to figure out who are in a critical path of execution, right? And the critical path could change, right? So if you look at 2, 4, 5, right? 2, 4, 5, they are the dependency chain of deciding if the iteration is going to be executed or not in the next run. However, that's only because right now we are assuming it only takes 2 cycles to fetch the memory, right? But saying that if right now my memory takes 4 cycles, like most of the processor would happen, right? Then one thing you could imagine is that for this instruction 1, instruction 3 has to wait at this point, 1, 2, 3, 4. Okay, actually this point to receive its result, right? Then the critical path would completely change, right? So sometimes without given sufficient amount of information, it's hard to judge where the critical path is. And it's really architectural dependent. And even though sometimes you think memory operations is the longest, but if you have cache, that would change, right? So the critical path analysis is actually one of the most difficult thing to do in performance analysis in code optimization. And without knowing the complete picture of the latency of execution, without knowing the complete picture of what your program structure look like, it's really hard to make it happen, right? So that's why we need this. And now I want to test if you know how to do this. So this is the linked list code. Which instruction, which line of code would determine the performance? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's take a look. Okay, so most of you think is C. So C is oops. C is the line of current equal to current next. Why? Can somebody give me the answer? Why is C the determining factor? It has to load memory, but that's not a sufficient issue. And that's not a sufficient reason, right? How can you convince me? Like previously, the last example, right? When we access memory, this is exactly the same pipeline, right? Then the memory instruction is not on the critical path, but why this one is on the critical path? All right, so just saying that memory instruction is not a good enough reason for that, right? Because the same pipeline, previous one, is on a memory instruction. Yes.
It needs to go through the memory stages before it can fetch it.
Okay, so we have, well, so there is a dependency here, right? But in the previous example, we have a lot of dependency in the graph. Dependency is on a critical path. Why this one is on a critical path?
Because it needs to determine it.
It's the only dependency. Okay, so here's the thing. How do you show that? Right? So here's the training that you have to receive, right? So you have to clearly state, right? And if you feel like you need to explain it in more detail, do it, right? So one thing I learned in my life is that if there is anything you think you should do to make it better, just do it. So I would say, well, there are things that we might feel lazy to do for this particular problem, right? For example, you can do this, right? Through drawing the register renaming pipeline, right? I see for every iteration, right? 5 is the last one to finish. And the reason why 5 cannot finish is simply because we have to go through the dependency chain of we have to go to this long dependency chain. So therefore, there is not really parallelism, right? And all this dependency chain is doing that pointer chasing stuff, right? Another thing is that you can also do data flow analysis, and it's even more clear if you do data flow analysis, right? You will figure out that for data flow analysis, right, there is a clear critical path showing up here, right? Everything goes through this one is the critical path, right? Everything goes through this 2 instructions in particular are the critical paths. And what are those 2? They are the instructions doing the pointer chasing, right? Like this instruction is actually getting this, and this instruction is trying to perform this operation, right? So you have to show this as a proof. Get it? Okay, and through this data flow graph analysis or through this critical path analysis, one thing you figure out is that, well, for this iteration, I have 5 instructions in total. But for the things, the performance is completely depending on a dependency chain of 1, 2, and the next iteration of 6, 7, right? You will figure out that for each iteration, it takes 4 cycles to execute on average, right? So turns out if each iteration takes 4 cycles and each iteration has 5 instructions, the average CPI for these pieces of code will be 0.8 for the given pipeline, right? And remember, what's the minimum CPI that we can achieve on this pipeline? 0.5. So we are far from there, right? If you have a code like this. All right. So, yeah. Now, so the thing is that the average CPI for this pieces of code would be 0.5. Okay. We go. All right. So now I'm going to show you a demo. So how bad is linked list performance in real? A lot of you like linked list, right? Especially those algorithm teachers, data structure teachers, they love linked lists. They want you to implement linked lists, right? I feel like but okay. So first of all, I want to make a disclaimer. I didn't say that those stuff are useless, but in terms of performance, you have to be really careful when you are using them. And for some reason, it's loading. Oh, no, this is assignment 4. Why? Okay. No, not this one for sure. Why am I? Uh-oh. Yeah, assignment 4 is up soon, so be prepared for that. What's today? Auto over programming. Okay, here we go. All right. Okay, this is supposed to be the content today. And then clear all outputs. Okay, I have, oops, clear all clear output. Okay, so I have a pieces of code that's doing linked list traversal. So for some reason, I think some of my updates are not saved. Okay, render code. Linked list, link list C. Okay, so here's the code. So I have two functions that I want to play with. One is the depth of the list, which is exactly the same linked list traversal code. And another one, okay, first of all, I have to say, these two pieces of code, they are not equivalent. However, I just want to let you know, given almost the same amount of work, what their performance looks like. So for this one, I'm doing things differently. And the reason is because I want to prevent some of the stupid compiler optimization. And the thing is, like for this particular pieces of code, I try to load the node value. So you know that we are still accessing the same array, but we try to access. So first of all, right, a few things that I'm doing here. I still check if the next pointer is null or not, like what we do here. And I additionally load the value inside this node. So actually I use the array to do more work than here, right? So if you consider instruction count, this function is actually worse because it's actually doing more things. And for this one, it just try to see how long the list is. And for this particular function, I have two pieces of code where if I set the list, which is controlled by the argument 3 as 1, then I would go through the linked list traversal function. If it's set to 0, I'm just doing the array function. So now let's run it. And well, ignore those, right? And now I finish running the result and I can show you the outcome. So as you can see, when the list is equal to 0, means that I am just doing array traversal. And as I just mentioned, because I'm doing more work, so it's not too difficult to imagine that my instruction count is increased. And the number of cycles is actually smaller than the one in list traversal. So the CPI is actually more than 2 times, almost 3 times better than linked list. And the execution time is indeed a lot significantly faster in our case, right? So this is an example that shows you how slow linked list is in real. All right. Okay. And again, as I just mentioned, if I want to optimize the performance, it's really important for us to understand what kind of bits that we are dealing with. So it's a good idea to look over what the modern processor pipeline looks like. So, so this is the Intel Skylake processor. So if you have anything before the 9th generation of Intel processor, I think it's the 6th to 9th generation of Intel processor. They are all similar to this Intel Skylake processor. And right now, with your knowledge, you will figure out that you understand a lot in this pipeline diagram, right? So this is the branch prediction unit, and this is the L1 instruction cache and decode unit, right? And also decoded iCache. So interestingly, right, in x86 processor, although it has the front end of x86 instructions, but internally, they would decode each x86 instruction into micro ops. So these micro ops are RISC-like instructions. So for example, a move instruction could be decoded into an LU instruction plus memory operation, right? So this or an exclusive or L instruction will be decoded as an LU instruction, a memory instruction, right? So this is what the decoded iCache is storing. So it's kind of interesting. The I cache is stored the original x86 code, and this one is trying to decode the x86 code into the micro ops. And then this is the storage, the internal storage of the micro ops. And this is the instruction decode queue, which try to further decode those micro ops and then allocate, rename, right? Retiring. So this is a renamed plus reorder buffer structure in Intel processor. And finally, there's a scheduler, try to issue instructions, right? You know everything here now, right? And well, looking at the pipeline, it has 4 issue integer pipeline, and it has 4 issue memory pipeline, right? So the most optimal case, you're able to issue 8 instructions in total in Intel processor. So you can imagine your CPI for Intel instruction, if you only have integer instruction, it could be 1/4 in the optimal case. If you only have memory operations, it could be 1/4 in the optimal case. If you have both memory instructions and integer instruction, then it will be 1/8, right? So this is the minimum CPI you can achieve on this processor. And this is the AMD Zen 2 processor, which is the assigned reading, and also the processor that you are working on for your assignment 3. And for this processor, again, it has a 4 issue integer pipeline, 3 issue memory pipeline. So the minimum CPI of this guy is 1/7. If you only have integer instruction, it will be 1/4. If you only have only memory instruction, that will be 1/3. So this is what we can achieve with modern processors, right? And again, if you want to fully utilize this pipeline, you have to avoid the data dependency chain. You have to make sure that you have sufficient amount of parallelism within your code. And this is the Intel Skylake processor as well, right? Which we already seen. And this is the latest Intel Alder Lake processor, the 12th generation processor. And well, they draw the pipeline even more complicated. However, here's a highlight. They have 5 issue ALU pipeline. They have 7 issue memory pipeline. So in the optimal case, you are going to get 1/12 as your minimum CPI in modern x86 processor for each core in Intel processor. So here, yes.
Question, will this change due to the type of the CPU, such as i9, i7?
No. So Intel, so for Intel processor, the only difference between i9, i4, i5, i5, i7, and i9 is the number of cores and the ability to support simultaneous multi-threading. So for this processor in particular, as long as they are using the performance core, the configuration is always like this. Okay, so looking over those pipelines, a few things that we are learning, right? First of all, modern processors, they all have those multi-issue pipeline with multiple functional units available. Like you always see multiple LUs, multiple load storage units, and they also have a dynamic auto-order scheduling unit to reorder instruction whenever possible. And there is sufficient amount of cache per processor. There are always branch predictors. So here's the bit that we're okay. So knowing this, how can we perform performance programming on modern processors? That's our topic today. And let me start with this example. I know a lot of you like LeetCode, so I try to rephrase the problem in the format of LeetCode. So pop count is a specific specific problem that tries to count how many bits in a given number is 1. And it's really useful for error correction, cryptography, sparse matrix multiplications, molecular fingerprinting, or if you want to use big vector to implement sustained data types or wavelet trees, right? So this is a very useful case. And here's the format in LeetCode, right? Given a 64-bit integer number, find the number of ones in its binary representation, right? Example 1, input this number, output 7, and you can see this number's representation is this. So you will see 1, 2, 3, 4, 5, 6, 7, 7 ones, right? So this is, and here's the driver code, right? And what you need to implement is this pop count function, right? So the driver code is trying to iterate through the pop. It's trying to give you this amount of input numbers randomly, and we call the pop count functions, right? So how are you going to implement this pop count functions? Okay, so here are 5 implementations that I have. Which one do you think will perform the best on modern processors? Oh, okay. Okay, looks like I only made 4 options for this. Okay, let me add one right now. Save. Okay, if you want to choose E, you can do it. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so this is what you guys think. Oh, okay. So 3 of you think it's E and B, C, D. They are all popular answers. So why don't you go ahead and discuss with your friend to see which one you think is the best one. Go discuss. Some noise. Which one is the best one? All right, let's wrap up in 15 seconds. Okay, so looks like after discussion, more of you think the answer is D. So, why? You just picked D. Why? Dependency of X. But this one also have dependency of X, right? Okay, I want to hear more. Okay, so say again.
The A, B, and C all have the dependency of X to determine whether the well will continue.
Oh, so you said for
all
the
this-
while here is all depending on X,
Yeah,
all right? And for this one, the for loop is not depending on X. Okay, so this one as well, right?
And
Ah,
we also have the dependency of the switch.
so dependency of the switch condition.
That's
I still want to choose E.
You still want to choose E. Okay. Why?
I don't know, but because due to the programming assignment, actually I do such an implementation to
Also, in your experience, E is better.
yeah.
Okay. What else? Okay, so the answer is D. But we want to dig into more detail regarding why. So first of all, right, for this 5 implementation, except for D, what's the second best one? C, and then where is your E?
I don't know, but if you said D is the best answer, so the second one must be C.
Okay, what else? And then who else? All right, you know, seeing is believing. So let's run the demo again. Oh, okay, so here is the code example we have. So we have pubcount.cpp, and this is the version A, which is the while loop with C plus equal to X and 1 and use shift, right? Looks very professional. You have bitwise operators, and the algorithm is so fancy, it's order 1. Right, and it's just 2 lines of code in a loop. It's so easy to understand. It fulfills all the standards of the good program. And it doesn't have additional iterations because whenever the X is 0, it terminates. What a perfect pieces of code, right? The second one, right, from a professional programmer's perspective, well, ugly, right? Like your loop is doing repetitive things, right? And I don't know why you are doing this repetitive things. And sometimes, right, you may do additional things which increase your amount of work and still depending on what. So the third version C, right? Oh, you use a lookup table, right? And it performs 4 bits at the same time. So the lookup table, it means that if you give me 4 bits, right? And if this 4 bits number is 0, then I would output 0. If it's 1, then it means that this 4 bits has 1 in it, right? And if it's 2, right? 2 is 0, 0, 1, 0. So there is 1, 1 in it. And if it's 3, it's 0, 0, 1, 1. So it has 2 1s, right? So if you, at the end, if you have 15, it's 1, 1, 1, 1. So that's why the table is constructed as 4, right? And I can do while x to do a table. And D is different from the while x, right? And the while x terminates whenever the value reaches 0. So for example, if you have a relatively small number, this while loop will terminate early. And for this one, it's a for loop. So no matter how small, how big the number is, it will always go through the loop for 16 times, right? So some of you might think, well, this is a terrible design of the code, right? Plus, there are so many memory operations. You have to access the table. The fifth one, right, is make the table a case, right? So if it's case 1 plus equal 1, right? So there's no memory access then, right? Everything is hard-coded, right? So this is another design of this pieces of code. Now, let's look at who has the best performance. Okay, so let's run it. Okay, take a while. Is it up and running? Okay, okay. So now we finish running version A. It takes 17 seconds. Okay, I was thinking if it's running, but apparently it's running, right? The version A takes 7 seconds. Version B take 14 seconds, right? So B is better than A, right? Now, C takes 7 seconds. Okay, twice faster with lookup tables, right? Okay, D is even faster than C, even though it sounds like the for loop does more work. And you love version E, right? It has been 6 seconds at least. So I don't think it's faster than D anyway. It should be more than 7 seconds, so it's probably not going to be faster than version C. Is it 14 seconds already? Probably, right? So version E is probably not going to be faster than version B anyway, right? And I think we took more than 17 seconds, right? So, version E, version E. How slow? Do you feel like it's already like minutes? What? No, there's no bug, right? So looking at the output, they all give you the same result, right? And it takes 1 minute and 8 seconds, right? And I didn't do anything to mistreat E, right? So everyone look at this, right? It's optimized 03, a fairly good optimization, right? So A, B, C, D, E, they are all treated equally, right? Okay, so why? 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 Tell me why, right? So let's talk about why. So first of all, why is B better than A? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Okay. C is the most popular answer, but you guys pick 2. Are the 2 that you have in mind is the same with the other 2 that I have in mind? Go ahead, discuss for 90 seconds. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, I believe C is the correct change. All right, so C is still the most popular, but what are the 2 that you have in mind? Okay, so let's go back to this question again. What are 2 that you guys have in mind? Why is B better than A?
It has less compare instruction.
Okay, so
Because
it
seems like you unloop the while.
So I unloop the while, right? So I potentially would have more or less.
Less compare.
Let's compare instructions. Okay. If the number is big enough, right? Okay. So B has lower dynamic instruction count. How about misprediction rate? It's about the same. Agree? How about fewer branch instructions? You think B is fewer? Okay, so you remove the compare instruction, right? So how about data hazards? Because the compare instruction is also okay. So the total source is just because you remove that compare, right? So okay, so oh, oops. Okay, so why is B better than A, right? So we have to look at this question in more assembly level, unfortunately. So here's the compiled assembly code for this particular loop. It has a, oh, I think I have, oh yeah. So for this one, right, if you use the optimal compiler, then it will generate this 5 lines of code for you. And for B, if you have to iterate the loop for n times, you will have like 5 times n instructions. And this is the code generated for version B. As you can see, it's an unrolled version. And sometimes, right, loop unrolling, the benefit is not just removing the jump not equal. There are more implications. So first of all, the benefit is that there is only one branch for 4 iterations. And the other thing, right? So in terms of instruction count, right? One branch for 4 iterations in A, and a total of 15 instructions are necessary to implement this 4 iterations. So on average, you only have 3.75 instructions in implementing per iteration, given the compiled code. Another thing that's also worth looking is, if you look at the register that has been used in the original loop, right? It's ECX, ECX, EDX, RAX. But if you look at the compiled code in the unrolled version, the first iteration using EAX and RD, well, the first iteration used EAX and RDX, right? And the second iteration, right, it used EDX, RAX, right? So compiler actually reorder. And the other thing is that you will see the move Q instruction, which is a memory access instruction from the second iteration, also get a chance to move up earlier, right? If you can execute a memory instruction earlier, you can actually make the memory access happen earlier to further avoid the data hazard, right? Because you started earlier, you schedule the instruction depending on it later. There could be an avoidance of data hazard, right? So from this one, you can see there are several benefits of loop on, right? If you keep going, you will find out there are several benefits of loop unrolling is that it indeed try to do this reordering all the time, right? So that's why it has lower dynamic instruction count, as we just analyzed. It has significantly fewer branch instructions because right now you only have 1 over every 4. And it also incurs fewer data hazard, which is because the fact that it can actually reorder the instructions. And we got some time, so we can potentially show you this demo, which is give you the proof of okay, let me do this. So we can actually use the tool perf, our good friend, right, to see if those numbers are really changing. So let me do this perf stat -a. Okay, so let me run these 2 programs. Oh, performance is limited. Okay, so what do I have to do? Okay, here we go. Oops. All right. Can I do this? Okay, so here I'm showing you a demo for this particular program by using the perf tool. This is the auto order programming. This is the pop count. Okay, so right now I can do perf stat -a pop count version A. All right, here is the version A. And it would take a while, 17 seconds as far as we remember. All right, so for this demo, right, you can see with version 8, we got 34 millions, well, trillions of instructions. And there are 65 trillions of branches. And the branch misprediction rate is actually not bad. It's 0.83, right? And now let's looking at B. Yeah, and the instruction per cycle is actually, so this is the flip of CPI. So it's actually 1/3. Not bad. Okay, but for instruction, for the version B, right? One thing you can find is that, well, the number of dynamic instruction is indeed a lot fewer, right? So from 334 to 290. Number of branches, wow, it significantly reduced from 65 to 18, right? And the misprediction rate, well, slightly lower, but I don't think it's really, really that much different, right? And the CPI is still about still slightly higher, right? So here's what you can learn, right? So the thing is that, well, if we can, look, that's how loop unrolling can help, right? First, you remove the branch, and second is that you also enable the chances of rescheduling, right? And with rescheduling, potentially you will get better, you can avoid some data hazards, right? So before you leave the classroom, several things I want to let you know. Assignment 3 due Friday, reading quiz due next Monday. Other than that, enjoy the rest of your week. If you want to go on strike, go ahead, do it. Other than that, but still don't forget to turn in your assignment. Other than that, enjoy the rest of your week.
We're 1,000 miles from comfort. We have traveled land and sea.